Hello everyone, and thanks for watching Edupedia World Videos. This is the second video in the chapter Alternating Current, and in this video we'll start combining different components that we studied separately in the previous video. Now, in the previous video we saw what the current is when we apply an alternating voltage to resistive circuits, capacitive circuits, inductive circuits. Right. Now our plan will be to see what happens when we have combinations RC, CL and RL and finally RLC. Now for these three cases we calculated the value of I0 and the value of phase. I'll just write the question again. We'll be given E is equal to E0 sine omega t, and we'll be given either an R, a C, LL or a combination of them, and our goal will be to write I as I0 sine omega t plus phi, and once we've done that we will have to find the value of I0 and phi. For R circuits, I0 was E0 by R and phi was 0. For C circuits, I0 was E0 omega c, or I'll write it now as E0 by 1 by omega c, and phi was pi by 2. And for inductive circuits, I0 was E0 by omega L and phi was minus pi by 2. Right. So these three we actually calculated directly. We wrote the equations and then we integrated or differentiated them to get the result. And what I was planning to do was show using the same method what happens for one of these, maybe an RC circuit, and then I would show you a quick and easy trick to be able to calculate I0 and phi for any of these. The problem, however, I have is I tried to calculate for an RC circuit in the way in which we did for RC and L circuits, but even for that circuit the mathematics is beyond your course. So I have no choice but to show you by using a standard trick which is taught in this chapter how to calculate these two quantities I0 and phi for RC, CL, RL and RLC circuits. But you'll have to take my word for it, that trick actually gives you the genuine answer, the same answer which you would get if you actually wrote the equation and solved it. But writing the equation and solving the mathematics of that is beyond the scope of your course, so unfortunately I will not be able to do that. I'll directly show you the trick. Right. So before showing you the trick, I'll just show some definitions. The first definition is reactance. Reactance is always defined for an element. What is an element? R is an element, C is an element, and L is an element. In LC circuits or CL circuits, you'll have two elements. You'll have C and an L. Each element will have its own reactance. Right. The reactance is written by X, and it is the subscript denotes for what it is. So X for R is R. Sorry, I'll write it on different rows. X for C is 1 by omega C, and X for L is omega L. And from this you can sort of see what XL really means. Reactance is just like resistance. It is the equivalent of resistance. If you just had the resistor, reactance was resistance and the phase difference was 0. For other elements, reactance sort of mathematically works like resistance. The only difference is there will be a phase difference. So the definition of reactance of an element simply is, if I0 is equal to E0 by something X, then that X is the reactance. And that's why you can see I wrote I0 here as E0 by 1 by omega C instead of E0 omega C, which are mathematically the same thing. So the reactance for the resistance is the resistance itself. The reactance for a capacitor is 1 by omega C. The reactance for an inductor is omega L. And for any of these three elements, the magnitude of current is E0 divided by the reactance. Right. And next, obviously, you have phase factor, which is 0 for resistance, pi by 2 for C, and minus pi by 2 for L. Now just like reactance, you have another quantity denoted by Z, which is called impedance. The difference is reactance is for an element, impedance is always for a circuit, for an entire circuit. So if you have, for example, an RC circuit, then R will have its own reactance, C will have its own reactance, and the circuit will have a net impedance. right? And the circuit will obviously have its own phase factor as well. By the way, from now I'll be writing phi r equal to 0, phi c equal to pi by 2, phi L equal to minus pi by 2. And this is just saying that if we only have an inductor, then the phase difference will be minus pi by 2. Right. Now let's get on to the trick. That trick uses the vector method. Right. So ultimately what our goal will be, earlier our goal was E is equal to E naught sine omega t, which means I is equal to I naught sine omega t plus phi, and we needed to find I naught and phi. Now all we'll do is, instead of I naught, we'll just replace it by E naught by Z, and we'll need to find Z. As soon as we found Z, we'll be able to find E naught by Z, which is I naught. So instead of finding the magnitude of current for a circuit, we'll just try to calculate the impedance for the circuit. Once we know the impedance for the circuit, then we'll use this equation to calculate the current. Right. Now the impedance for a single element is called its reactance. Impedance for more than one element is called impedance for the entire circuit. Right. So let's start from the beginning. What happens for resistors? For resistors, you have a reactance which is equal to R, and if, so I'll just write it as XR, and if the circuit only has a single resistance, then the impedance of the circuit is also R, because it only has one element. When we have more than one element, we'll see how to combine them, but for a single element, the impedance is the reactance, right? And phi is equal to 0. So I can write a resistance in a vector form, and this is not strictly vectors in that it has a magnitude and direction. This is vectors in the same way we used vectors for simple harmonic motion. When we added two simple harmonic motions, we got a third simple harmonic motion, and we saw that the resultant seemed mathematically similar to adding two vectors. So we use the vector method to calculate the resultant of two simple harmonic motions, even though simple harmonic motions have nothing to do with vectors. Similarly, we'll use the concepts of vectors because they're mathematically equivalent, but never make the confusion that capacitance or inductance or impedance or any of these are vectors. These are all scalars. The only vectors are magnetic field and electric field, right? And obviously magnetic and electric forces, right? So in this case, X will be equal to R and phi is 0. We'll represent it as this. We'll represent it as a vector which has a magnitude R and direction 0, that makes an angle 0 with the x-axis, right? So this is the vector for reactance of a resistance. For a capacitor, chi c is equal to 1 by omega c and phi is equal to pi by 2. So how will we represent that? We'll just represent that like this. The angle will be pi by 2, the magnitude will be 1 by omega c. This is the origin. So the reactance for resistor can be represented as a vector of magnitude R, making an angle of 0 degrees with the x-axis. Capacitance, vector of magnitude 1 by omega c, making pi by 2 with the x-axis. Inductance, I'm sure you guessed it by now. XL is omega L, phi is minus pi by 2, and we'll be representing this like this. Going from here to here, an arrow which has a length omega L and makes an angle minus pi by 2 with the x-axis. So now Z is sometimes thought of as a vector. Z and X, now you need to start thinking of them as vectors. Even though they are not vectors, just like we thought of simple harmonic motions as vectors, we'll think of them as vectors. In particular, we'll add them the way vectors are added, right? So just let's see what happens when we have an RC circuit. And again, I do apologize because ideally I believe the best way to teach, and what I would like to do is show you an RC circuit, show you X and phi for that using this trick, and show you X and phi for that using the original method, long method, and show you that they give the same result. But unfortunately, like I said at the beginning, I cannot show you that for the long method because that's beyond the scope of your course. So for an RC circuit, all we'll do is we'll add these two. But we'll not add them directly, we'll add them like vectors, right? So we'll add the vector reactance of R and the vector reactance of C, and the net resultant vector will be the vector impedance of the RC circuit. So I'll write that first. Vector is just vector reactance plus vector reactance gives you the vector impedance. So how does this work? If you have an RC circuit, that means you'll add these two vectors. So you will have one vector, magnitude R, pointing towards the right. Then you'll have a vector, magnitude 1 by omega c. I'll just write it as xc for now. Right, xr is equal to r, that's a trivial equation. I'll just write it as xc. The magnitude will be 90 degrees. What is the sum of this? The sum of this will be a vector z making an angle phi. And this z and phi will be the actual z and phi for the RC circuit. So what will be the value of z? Z will be root of r square plus xc square, or root of r squared plus 1 by omega squared c squared. And what will be phi? It will be tan inverse of xc by r, right? So phi will be tan inverse of xc by r, which is equal to tan inverse of 1 by omega rc, right? So what does this tell us? I'll just try to write this in a bubble here because I don't want to erase this first image right now. So it just tells us that if we have an RC circuit with E is equal to E naught sine omega t, then the current is equal to E naught by Z sine omega t plus phi, where phi is equal to this and Z is equal to this, right? So now I hope you understand it's simple enough. We represented the reactance of each individual element by a vector. Then whenever we add two elements in a circuit, we add their reactances like we would add vectors. The resultant vector would have a magnitude equal to the net impedance of the circuit. The resultant vector would make an angle with the x-axis equal to the phase factor of the circuit. Now I'll restart this and show you again from the starting. So RC circuit, it will be like this. This will be R, this will be XC, this will be the net vector sum Z, angle phi. So Z is equal to root of R squared plus XC squared. Now I'm not going to write the values of XC. Phi will be tan inverse of XC by R. What happens in an LC circuit? Let's do LR first, that's easier. What happens in an LR circuit? In an LR circuit, R will be here and L will be in the downward direction, but the value will be chi here. Now you see why we have reactance, because we can't add resistance to an inductance, but we can add resistance to something which behaves like a resistor, has the same dimension of resistance. And XL is omega L, right? So the sum of them will give me this angle. This will not be phi actually. Phi will be the negative of this, and this will give me Z. So for LR circuits, Z is equal to root of R squared plus XL squared, and phi is equal to tan inverse of minus XL by R, or you can say it is negative of tan inverse XL by R because it's in the opposite direction. Finally, what happens with an LC circuit? LC circuit is easy enough. This is XC, this is XL. We'll just add them up. So Z will be equal to XC minus XL or XL minus XC, whichever is greater. So I'm going to use the magnitude XC minus XL, and phi will be equal to pi by 2 if XC is greater than XL, and minus pi by 2 if XC is less than XL. I apologize, my C and X's are looking somewhat similar. Right, so that's it. All you need to do is add the vector reactances. You'll get the net vector impedance. The magnitude will be the impedance. The angle made with the x-axis will be the phase factor. Once you've calculated the impedance and the phase factor directly you needed, impedance gives you, with using E naught by Z, the magnitude of the current. And let's move on to the most important of all, LCR circuits. So in an LCR circuit, you will have R here, you will have XL here, you will have XC here. So what will the sum be? We'll just for a second assume that XC is greater than XL. And I'm sure you'll be able to deduce what will happen if XC is less than XL. If XC is greater than XL, let me just draw it bigger like this. Right, this whole will be XC, this is XL. So this much might be XC minus XL, right? And if you add this like this, then it will go here, this will be Z, this will be phi. What will Z be equal to? Z will be equal to root of R squared plus XC minus XL. And phi will be equal to tan inverse of XC by R. XL whole squared. This is C. And phi will be tan inverse of XC minus XL by R. Now if XC is less than XL, then it will point in the downward direction and phi will be negative. This term will still be the same. Right? So I'll just take one of these as an example to show you where we started from. Let's do the simple RC circuit from the beginning. So that means we have an alternating current source, then we have a resistance, then we have a capacitance. This alternating current source is E0 sine omega t. This is R, this is C. We know that I will be of the form of I0 sine omega t plus phi. All we need to do is calculate I0 and phi. So we'll write the reactance of both of them. R will give me a reactance like this of R. XC will give me a reactance like this of XC. Add them up, it will give me net Z and phi. Z will be equal to root of, we just did this all now, plus R squared. Phi will be tan inverse XC by R, and the final equation will simply be I is equal to E0 divided by Z sine of omega t plus phi. So phi we get from here, after we get Z we get I0 from here. The same thing we do for the others, right? The one important thing here, if you have an LCR circuit, then the impedance and the reactance, remember, both of them are like resistance. The greater they are, the smaller the magnitude of the current is, right? So if we have a smaller impedance, that will give us a greater magnitude of current, right? What would happen if XCL, XL would be 0? Would be equal to each other. If XC and XL would be equal to each other, then XC minus XL would be 0. The impedance would be minimum. The current would be maximum. And not only that, but the impedance, but the current and voltage would have the same phase because the phase difference would be 0. Right. Now for a second, let's look at a simple LC circuit. In an LC circuit, we have XC up, XL down, Z is equal to mod of XC minus XL, and phi is equal to either pi by 2 or minus pi by 2. In that case, we can see if XC is equal to XL, in that case, there is no determinate phase difference, we cannot determine it, and Z is 0. So we reach the singularity where the resistance, the analog of resistance becomes 0. Now, technically it does not really ever become 0 because energy is dissipated in other ways and you do not have an infinite amount of current, but practically it is very, very large. So when you have XC equal to XL, then you have large current. We would say infinite current, but again there are many things which we have to consider when we go from an ideal case to a real case, such that there are no actual wires which have zero resistance. Even the attaching wires would have some resistance, so you would have to take care of that as well. But again, I really apologize. I'll make an effort to make my L's and C's look. If this is true, then we have a large current, and that is called resonance. Similar to SHM. In SHM, the resonance was when two frequencies were similar or close to each other, then we had resonance. Here the two reactances have to be close to each other, then we have resonance. What does this mean? 1 by omega C is equal to omega L, which means omega is equal to root of 1 by LC. So if you have an LC circuit and you can change the angular frequency of the voltage, then if the angular frequency of the voltage is changed to be equal to this, that is when we have resonance, and so this is called the angular resonant frequency. And since this is omega mu, which is omega by 2 pi, that is 1 by 2 pi times root of 1 by LC, this is called the actual resonant frequency. One of the most common sources of error I've seen among students is confusing angular frequency and frequency. Remember, they are different. Angular frequency is omega, frequency is mu. Angular frequency is radians per second, mu is revolutions per second, and they have a factor of 2 pi in them. Right, angular frequency is radians per second, nu is simply per second or hertz. So in this case, you might have a question in which you might have an alternating current and you'll be given two values, a value of an inductance and a value of a capacitance, and you will be asked what should be the frequency of the alternating current so that you will have maximum current. Maximum current means resistance, means the frequency should be such that these two should be equal. I generally try to remember as few formulas as possible. So even though I do remember this because I've seen this many times, ideally I don't want you to try to remember this or this. Ideally I want you to remember this concept. And if you remember this concept and you remember the formulas for each of them, then you remember all of them. There's no need to remember the impedance and the phase factor for LC, RC and LR and LRC circuits. Ideally, you should remember these for L, C and R separate circuits, and you should understand the concept of how to add them together. Okay. Just one or two small things are left in this chapter. One thing is, what is the power dissipated in the net AC circuit? Now when we talk about power dissipated, this means the power dissipated by the battery or the EMF providing source, right? There will be some power dissipated through resistance, there will be some energy stored in an inductor or the capacitance. We are not talking about those, we know how to calculate those individually. Right now we'll be talking about how much energy or power is delivered by the EMF generating source per unit cycle, right? So what is the small amount of work done by the EMF producing source? That will be the EMF multiplied by the charge, right? So that will be E multiplied by dq. That can be written as EI dt, right? Now if you want to integrate it and get the total work, that will be integral of EI dt, that is E naught I naught sine omega t plus phi dt. Now you know how to do this integral, but there's no need to do it. It might create a complicated expression. If you want to try, you can do it. But if we actually do this for one single cycle, then you can try to calculate it. It will be easy, and the answer will come out to be half E naught I naught cos phi t. This is the work done. So what is the power generated in one cycle? W divided by the time, right? So power generated by AC source is equal to half E naught I naught cos phi. Or another way of writing this is E RMS I RMS cos phi. Because E naught by root 2 is E RMS and I naught by root 2 is I RMS, right? So E RMS I RMS cos phi. We see that if phi is 90 degrees, that means if the phase difference between the current and the potential difference is 90 degrees, in that case there will be no power that will be dissipated by the energy source. All the energy, in that case the power will be shifting from the energy source to the capacitor or inductor back to the energy source, because 90 degree will be in a purely capacitive or inductive circuit without resistances, right? One small definition, cos phi is called the power factor. And there's one small thing remaining, which is, what do we do when we need to reduce the current across a given region? Potential difference across a given region. Let's say we have a battery or an AC source. Here it doesn't matter. Let's take an AC source because we are doing AC right now. And we have a resistance. And we wanted to reduce the current across this resistor. One way to reduce the current across this resistor would be to add another resistor in series with this, right? The more resistances you add, the smaller the current will be. Another more creative way to do this is using something called a choke coil. And this term you might have used if you ever heard people fixing tube lights, because this does exist in your everyday use tube lights. They do have a choke coil. In a choke coil, what we do is, our goal, remember, is to reduce the current through this resistance. Let's say the resistance can only take a certain amount of current, beyond that it will burn. So we don't want the current to be more than that, right? So instead of attaching another resistance, which is one way, another way could be, we could attach an inductor here. If we attach an inductor, then the net current will be E naught by root of R squared plus omega squared L squared. That will be the net current, right? So what will be the potential difference across this one? It will be this multiplied by R. So we see that we both reduce the potential difference across this one and the net current. Now, What is the advantage of doing this as opposed to a resistor? If you were to add another resistor, in that case, the power dissipated would increase, because every resistor you add is going to ultimately dissipate some power, and you would need to give a larger amount of power. However, if instead of a resistor you add an inductor in series, then inductor does not dissipate any power. It absorbs and stores some energy, and then it gives back that energy. Half Li squared is the energy stored in an inductor at any time, right? So that is why we use a choke coil, in that we have, and the inductance is usually large compared to the resistance. So by attaching an inductor in series with the resistance, you can reduce the current in the resistance without dissipating any extra power. And that is why you have choke coils that are used in many everyday household items. Okay. This completes alternating current. Next we'll move on to the study of electromagnetic waves, which will be the final chapter in electromagnetism. Thank you.